Thank you for the organizers for having me here and to talk and to give me the chance to talk about my work that actually started as mine and Brandon King's master thesis during our time at Sussex. And we are really glad that we continued working with Daniel and Manuel. And then we have something that we are like proud of. We are really happy about it. And now I have the chance to show it to you. So, matter spectral functions from quantum gravity. And so, let me quickly start by talking about the status of the paradigm that we all work in. And say that we have reached the point where we have numerous and numerous amount of computations that show the UV fixed point for gravity, and then simultaneously we have countless tests for compatibility with the standard model. So we have reached the point where we can almost strongly say that we can transition quantum gravity from being perturbatively non-renormalizable to being non-perturbatively renormalizable. Of course, we know this, but the reason I say almost is because we do have certain problems that we need to address, and two of these would be the central stage of this work, and these are the problems of unitarity and of the Lorentzian space-time signature. To explain unitarity and why its status is not fully clear, let me give the example of quadratic gravity, which is actually perturbative gravity, but it has a striking feature that the higher curvature term leads to the following structure of the graviton propagator, where this second term has the odd sign, and this directly leads to the massive ghost shown by Stelle in their work, and this directly leads to the spoilage of unitarity. And so, when we translate this problem to the paradigm of the asymptotic safety, we have to ask the question: what would happen at the UV fixed point, where we would technically need to have all of the curvature terms that are compatible with the symmetries at the fixed point. So of course, this gives us a paranoia that something might go wrong, something may lead to the spoilage of unitarity, just as how it happens with quadratic gravity. Um, there have been some positive works which actually show that these superficial ghost degrees of freedom that may show up actually get nullified when we compute the fully dressed propagator and reach the full truncation. So it is definitely a good direction that we are heading towards, but we still need to do a lot of work. And in my opinion, what we really need to address the question of unitarity is a proper non-perturbative Lorentzian framework. Um, which brings me to the second problem, which is of the Lorentzian space-time signature. And this is a problem mainly because the Wick rotation from Euclidean to a general Lorentzian manifold is not fully known. And this typically leads to a lot of computations performed within this field to be in the Euclidean setting, which also means that the output that we have gotten is in terms of space-like momenta, but what we really need to address unitarity is time-like momenta. And so, in order to do this, we need to take steps towards this direction. And before I get to the first major step, let me quickly talk about spectral functions, which are the main objects that we are computing here and the Källén-Lehmann spectral representation. So of course, we have the propagator, which is supposed to follow a Källén-Lehmann spectral representation. And once it does, we have the propagator defined on both space-like and time-like momenta. And then from the propagator, we can compute the spectral function by taking the branch cut on the time-like axis. And then the way the Källén-Lehmann spectral function is constructed, it makes sure that once we have a stable particle, we have its spectral function to be of the structure on the left, where we see the striking features, first of which being the delta peak, which represents the on-shell particle. And then we have a multi-particle continuum, which represents the quantum fluctuations. Then thirdly, we have the property that having a positive semi-definite spectral function is directly linked to the idea of unitarity. So we would really want spectral functions of a propagator to be positive semi-definite, along with having these features to make some solid deductions on the status of unitarity. So what I really want to say is that these are powerful tools that we should definitely use to take steps towards the problems at hand. And with this, I show you one of the first major steps that was taken in this direction, which comes from the paper by Daniel, Jan, and Manuel, which actually put forth a Lorentzian non-perturbative framework, which they used to compute the spectral function of the graviton on the flat space Minkowski background. And so and then computed the spectral function, which has these tracking features that we spoke about, mainly the on-shell delta peak, which is now at vanishing spectral values, and then we have a multi-particle continuum. And then the most non-trivial part is that this spectral function, of course, followed the Källén-Lehmann spectral representation, which is a great thing. And this means that the door has been opened for Lorentzian computations. And now what we really need to do, or really what we would want to do, is to have matter fields into the picture. So we of course ask now the question, which sectors do we want to work in as the second step in this direction? And what we choose in this work is the U1 work with this model is because we know that without gravity in the standard model, these sectors do not have a UV completion. But on the other hand, we know that photons and the Higgs field are present in real life. So of course, there is some sort of questions that needs to be answered. And then on the other hand, very promising works have shown that when you add quantum gravity to this picture, it can actually lead to a UV completion for these sectors. And this you can see through these plots, which show the top Yukawa and the hypercharged coupling, where quantum gravity fluctuations actually prevent the Landau poles and then can lead to a UV safe fixed point where from which you can have a predictive trajectory, and then eventually seeing that there can be a UV completion with the help of gravity. And so since we obviously know now that gravity and these sectors have some sort of compatibility with each other, we of course would like to see how these particles would behave, how their physics would behave by computing their propagators and their spectral functions and like seeing their time-like momenta. And so now that the goals have been set, which are now to compute the spectral functions of the gauge field and the scalar field, let me talk about the mathematical toolkit that we use within this work, which is the functional renormalization group that we all know. But now we have a small modification that we have to make. And this is because this the dispersion relation that we use is not compatible with the Källén-Lehmann spectral representation at finite k when used with the typical choice of regulator that we have in the FRG. And this is because a typical regulator would produce cuts and poles in the complex plane, making it not compatible with the Källén-Lehmann at finite k. To note that we can still perform the analytical continuation as k tends to 0, but of course we would want to have it for all of the RG scale. So in order to do this, we need to make a clever choice of the regulator. But then we know from this diagram that there is no regulator present that satisfies all of these three properties simultaneously. So whenever we choose one, we need to sacrifice one of these properties. So for the purposes of this work, we would be taking a regulator which follows the properties of Lorentz invariance and causality that leads us to the obvious choice, which is a Karen-Zemanzik regulator, which for bosonic fields is defined as this. And then for fermionic fields, we have it defined as this. Now, you can see that this regulator simply shifts the momenta from p square to k square to p square plus k square. And that means that there would not be any cuts and poles produced when used in conjunction with the Källén-Lehmann spectral representation. And that means we can use it at finite k. But there is a caveat and caveat B that since we would be sacrificing one of the three properties, this time it would be the property of finiteness. And so since we would be sacrificing the property of finiteness, the UV divergences that are regularized in the FRG would now resurface during our computations of the flows. So we need to compensate for these. And we do this by making a modification to the Vectoric equation, which comes in the form of this term in the red, which we are calling as the flowing counter term. And then we use the flowing counter term to regularize the UV divergences in a manner that is not too different from how we do it in standard KFT. So we use dimreg in 4 minus 2 epsilon dimensions to regularize them and then use these following renormalization conditions at vanishing momenta to now cancel the divergences and have finite flows. So now that we have talked about the toolkit, let me talk about the technical pieces and the approximations that we have done in this computation, starting from the flow of the between the spectral function and the propagator. So we use it and then we take its flow, by which we get that the flow of the spectral function is not dependent on the flow of the two-point function of the specific field. And this flow of the two-point function will be the main object that we will be computing right now, which is represented by these set of Feynman diagrams, where you can see the flow of the gauge two-point function and the flow of the scalar field two-point function. Throughout the work, we would be calling the first two diagrams as the gravity diagrams, and then the third diagram as the fermion loop or simply fermion diagram. Um, we, of course, have the flowing counter term, which we spoke about, that we would use to regularize the UV divergences that would resurface due to the choice of the Källén-Lehmann regulator. And then finally, we see that we, of course, we also have a fermion number, which we would later use as a free parameter to make certain deductions. Now, let me say that the way we solve these flows is by taking these lines, taking the propagators and replacing them with the Källén-Lehmann spectral representation. And that means that this gives us a very complicated set of differential equations that one really needs to cleverly solve because of how massive things get. And we do this by first taking a parameterization for, oh shit, sorry, for the spectral functions, where now we see that we have three features, one being the on-shell delta peak, and then we have two multiparticle continuums, one from the gravity diagrams, and then the other from the fermion loop. Both have different thresholds, so they both start at different values proportional to their respective masses. Now we use this parameterization and we plug it in to this flow, and then we now compare the left-hand side and the right-hand side to first get the flows of the mass parameters and the couplings. So now let me talk about the approximations that we use. Firstly, let me say that the mass parameters are dispersed in this way, where the first terms are a direct result of the choice of the regulators. Now that we have the mass terms, I talk about the approximations that we used to cut down a lot of heavy computation load. The first one being that we are neglecting the feedback of the continuum in the flow equations. And then second, on a similar note, we are neglecting the feedback of the fermion loop in the flows of the mass parameters. And both of these choices really cut down some heavy load and help us reach our goals faster. So then thirdly, we are using a very simple trajectory for the fermion mass parameter, but then still we have these two factors, C1 and C2, which now we dial in to set the value for the IR fermion mass, and then it's a UV fixed point. Then let me talk about the final technical piece in this computation, and that is, of course, the beta functions for the matter couplings, which we model after the hypercharge and the top Yukawa. Here we see that without the contribution from gravity at leading order, we would have the Landau poles, but then with gravity contributions that are now stored into these functions, the fg and the fy, we can now prevent that Landau pole and have the trajectories go to a safe or a free fixed point. I must say that these functions are typically dependent on the mass parameters of the graviton and things, but then at leading order, we can take them as just numbers so that we can now model these trajectories so that we either have a safe trajectory or a free trajectory, and then we can use these to then substitute back into the computation for the flow of the spectral function and to now see how the spectral functions change when computed using different coupling trajectories. Now that we have the technical pieces set, let me show you the things that we got, starting from the fixed points of the mass parameter and the coupling, which we get as these values. And when we use these to compute the anomalous dimensions, we get their fixed point values to be all positive. And this is something that would later play a role when we talk about the scaling of these spectral functions. Uh, but of course, these values on their own may not mean much. So to give them context, we compute the critical exponents, which, given the convention for the stability matrix, we get four relevant directions for these fixed points. And that means that we can now choose the IR values of these parameters for our convenience, and then use them to compute the trajectories that will lead to these same fixed points. So we do this to get the following trajectories for the mass parameters, and we also compute the wave function renormalizations. For the mass parameters and the coupling, we see that they scale as k square in the IR, and then beyond the Planck scale, they settle at their UV fixed points. For the wave function renormalizations, they have a scaling of k to the power minus the anomalous dimension fixed point, and then they neatly lead to a normalization of 1. Now, let me say again that because of the four relevant directions, we can set the IR values of these parameters. And so we do this by of course, setting the Newton coupling, which would go, the mass parameter of the graviton would go to the cosmological constant. The photon, we keep it as massless, and the scalar mass parameter, we can set it to a finite value. But again, since we can use our convenience, we set both the cosmological constant and the scalar mass to 0. Uh, now, then we have these trajectories, and then now what we have to do is feed them back into the flow of the spectral function, and then now use them to compute the spectral functions for both the gauge and the scalar field, which is the main goal. And we do this to get the following spectral functions, which we can see here. The red one is for the gauge field, and the black one is for the scalar field. So of course, we have some handful of features. But first, I must say that the most non-trivial thing being that both of these spectral functions follow the Källén-Lehmann spectral representation, which is a good thing. And we are happy that this came out this way. But then we also have, of course, the features such as the on-shell delta peak at vanishing values for both functions. And then we have our two multiparticle continuums where the fermion loops continuum starts at 2 times the fermion mass the fermion mass, which is set to this value, which leads to this first bump in both of the spectral functions, which says that this is where the fermion loops continuum starts. Uh, we also note that these functions are computed by setting the fermion number to 1. Next, we note that since we had found that the anomalous dimension fixed points to be positive, this leads to the fact that the scaling of both of the spectral functions is slower than the free propagator, and this directly leads to a consequence that within these approximations, these spectral functions are no longer normalizable. But the most striking feature of these functions is the fact that we have a sign change around the Planck scale. So first we see that before the Planck scale, we see that the spectral functions are behaving as we would want them to for photons and scalars. But then as we reach the Planck scale, where quantum gravity starts to become prevalent, it does something and leads to a sign change. which directly leads to these negative parts that we show in the dashed lines. But now, what does this mean? Since we have said that the positivity of a spectral function is directly linked to the unitarity, so does this mean that all hope is lost and then we now need to do something different? Well, not really, not quite so. And it's because these spectral functions were found to be gauge dependent, which means that they are no longer the observables, and which means that we cannot make a solid deduction about unitarity from these. We see this gauge dependence directly when we compute the IR, EFT expressions for these spectral functions, where we see that these are dependent on the gauge parameters of the gravity sector. We also note that the U1 gauge parameter drops out, so it's no longer a part, and it's only the gauge parameters of the gravity sector which play a role. Quickly, we also note that the IR value computed from this compares to the numerical spectral function that we computed by the error of just 8.4%. So it's nice. But like really what I want to emphasize is that since these spectral functions are gauge dependent, we cannot make a solid deduction on the status of unitarity. So what can we do then? So of course there are long-term things that we can do to assess this problem, but there are still things that we can do within this gauge choice. And then we can ask the question whether within this gauge choice can we do something to restore positivity, or rather see that can there be a scenario where these spectral functions can become positive. And so we do this by dissecting both spectral functions of the gauge and scalar field into their specific diagrammatic contributions. So of course, we have now three diagrams, the sum of which leads to the total spectral functions. And then each diagram is from each Feynman diagram. So now first we see the gravity diagrams first, where we note that the first diagram contributes to a fully positive contribution, but then the negative parts are coming from the second diagram, which is the one which has the matter line regulated. So we can look at this and be like, can there be a scenario where the first diagram dominate the second diagram and nullify the negative parts, giving us a positive spectral function? And we can do this by first writing the UV structure of both of these diagrams, the diagram 1 and 2, in terms of their scalings and the anomalous dimension fixed points. And now we can take the anomalous dimension of the graviton to be a temporary free parameter and then do the algebra such that the first diagram dominates the second diagram. And we see that if we were to have a positive spectral function for the gauge field, the anomalous dimension of the anomalous dimension of graviton, its fixed point needs to be less than 0.3, whereas for the scalar case, it needs to be less than minus 54. So already we see when we compare it to the actual value, which is 0.96, we see that this positivity might be possible for the gauge field, given the fact that we might do some corrections and maybe we have the approximations. So it might be possible that positivity may be restored for this gauge choice, but then for the scalar field, there is no way. It's too far away from the actual value. So the scalar field spectral function can not be made positive within this gauge choice. Now, we can do the exact same thing with the third diagram, where we first note that the fermion loop's contribution to the spectral function is fully positive, as we expect, and the continuum starts at the threshold of 2 times the mass, 2 times the fermion mass, which leads to two scaling regimes. First, which scales as the free propagator below the Planck scale, and then after the Planck scale, we have the scaling that is similar to the spectral functions in the UV. So now, since this is fully positive, we again ask the same question, whether somehow this contribution can be strong enough so that it nullifies the negative parts of the first two diagrams. And we do this again by first writing the UV structure of the fermion loop in terms of the matter couplings and then the fermion number. And then we ask the question that maybe we could add more fermions to the picture, and then maybe more fermions can lead to a positive spectral function. So we do the algebra comparing it to the UV structure of the gravity diagrams, which is now in terms of the Newton coupling, and then we find the following ratio for the gauge field and for the scalar field. So seeing this, we already see that the spectral function being positive from the fermion loop is not possible, since if we were to have this, we would either need hundreds of fermions or need a very, very non-perturbative values for the hypercharge and the Yukawa coupling. For the scalar field, it's even worse, where the fermion number needs to be in the orders of thousands. So we rule out the possibility that the fermion loop can nullify the negative parts. Next, I briefly show you what happens when we use trajectories for the couplings that are not safe, where we see that when we do this, the UV scaling of these spectral functions, the main change that happens is that the UV scaling of these spectral functions shift by this factor, which is given by the critical exponent of these coupling beta functions. And this we see in these plots, where now the solid line represents the spectral function computed using the asymptotically safe trajectory, and then the dotted lines, these are spectral functions computed using different values for the Fg and the Fy, which leads to free trajectories and which shift the scaling by this factor. Okay, so now that we have seen that these spectral functions of the gauge and the scalar field are gauge dependent, and that positivity is not likely possible to be in this gauge choice, what is the next step? What is it that we can do? So what you can do is try and compute scattering amplitudes. And for this, we look at form factors, which are which can be defined as part of the quantum action to hold the knowledge of your quantum fluctuations for, in this case, the 2-point function, where now the form factor for the scalar field classically would go as p square, and then for the gauge field, the form factor would go as 1. These form factors are also equally powerful tools, similar to spectral functions, but these form factors can now be directly used to compute amplitudes, which we might need to do to actually get rid of the gauge dependence. And so we now compute these form factors by using these relations that connect the spectral functions to their respective form factors. And we use this relation to get the following form factors for the gauge field in the red, and then for the scalar field in the black. First, we see that we have in the IR, the gauge field form factor goes to the classical structure of 1. And then for the scalar field, it goes to the classical structure of p square. But now we have a striking problem. We see that both form factors have a divergence, which again leads to a negative parts that are shown as dashed lines. And now this is not something that would we want, right? Since we would use these form factors to compute amplitudes, and having a divergence is no good. We note that these divergences are because of the sign change of the spectral functions. And so we now ask the question of like what we can do regarding this. And then we really look into scattering amplitudes more and what we can do when we write them out. So here we see the example of a fermion-fermion scattering, where we can roughly write it as the product between the vertices and the now fully dressed propagator. And now we note that in this work, we have basically computed this middle term, which is the full propagator, in terms of the full spectral function of the gauge field. But we of course have found this to be a gauge-dependent quantity, and then we of course have found its respective form factor to our divergence. So we know that what we have not done is to compute the full versions of these vertices, since we have just used the classical versions to compute our spectral functions. So what we really want to say is that we would want to compute in the future these full vertices, which would that would give us the expressions that we expect would cancel out the gauge dependence and the divergence, and would finally lead us to a finite result that is not dependent on a gauge parameter. And then from this, we can finally make a solid deduction on the state of unitarity on these sectors in conjunction with gravity. So I now quickly try to summarize what we have done. So mainly, let me start by saying that the goal of this work was to compute the spectral functions of the gauge field and the scalar field, since we know that these sectors are not really complete in the standard model without gravity, but then with gravity, these sectors have AUV completion. And now, since we had a Lorentzian setup, um, which was brought to us by first steps taken by people, we now set out to use that Lorentzian framework to compute the spectral functions of the gauge and the scalar field. And we have done that. And the most non-trivial part is that both of these spectral functions have a Källén-Lehmann spectral representation, which is a non-trivial and good thing. But on the flip side, we note that these spectral functions have a sign change due to the contributions from quantum gravity. Um, but luckily, since these are gauge dependent, we say that this does not lead to a loss of unitarity. And we say that we would now want to promote them to scattering amplitudes, for which we computed their respective form factors. But also on the flip side, we found them to be divergent. But in collection of these factors, we say that we need to really look for in the future to use this non-perturbative Lorentzian framework further to compute the full vertices, their form factors, specifically the 3-point and 4-point functions. And then we expect that when these are used in conjunction with the 2-point function, that we would get a finite result for our scattering amplitudes. and with which we would be able to make a solid deduction on the status of unitarity and push this question further. And this, thank you. I don't have a thank you slide, sorry. But yeah.
All right. Thank you very much, Varun, for the nice talk.
Yes, thank you.